Hello and welcome. This is SFU Math 152. My name is Brenda Davison. We're now going to cover today in this lecture section 6.1 and 10.4. So both these are common in that they're both finding area between curves. 6.1 is doing it in rectangular coordinates, and then 10.4 is doing it in polar coordinates. So that's why they are together here in one lecture. So we'll actually see some applications of why you'd want to do this as well. Okay, so what we're going to do is first do it in a rectangular coordinate. So that's the X, Y, and Z coordinate system that you're more typically used to. And what the idea here is that we want to find the area between two curves. And so we imagine one curve with equation f of x and another curve looking somehow different with an equation g of x. And we want to find what's the area between those two curves. So I don't think it's much of an extrapolation to be able to see how you would do this. And that is, so you could recall that this here, the integral from a to b, let's put where a and b are, a and b, the area of the integral from a to b of f of x dx, that measures the area between f of x and the x-axis. That is, of course, if f of x is greater than 0 on the interval, which in this case it is. And similarly, that's what g of x would measure, the area between the function g of x and the x-axis. So it's not, I don't think it's hard to imagine that the area between these two curves, that the area, so let's just put between. So I mean, what I mean there, the area between f of x and g of x, which is what I've shaded there with those little diagonal stripes, that is the area under the f of x curve minus the area under the g of x curve. And we could, of course, using our rules of integration, put that together, and then that would be into one integral, and that would be the area, or it would be the integral from a to b of f of x minus g of x dx. So we could compute the area between those two curves. This is actually a true statement even if g of x was below the x-axis, this statement here, the area between the two curves. Let's just see what that would look like. So if I were to draw some g of x here, some f of x here, and then I was to draw some sort of g of x down here, g of x is not above the x-axis, and I wanted to get the area between here, like that. It will, this formulation of how to do that will still work. And here's sort of a geometric intuition of why. I would just imagine here, going back to the definition of the definite integral, and I would imagine a representative rectangle here. Okay, so the height, and then I would have my little sampling point here. That would be, that little point there would be xi star. So I'm looking at the ith rectangle here, and there's the sampling point xi star. And then I would look at how would I calculate the height of this rectangle. So the height would be f at xi star minus g at xi star. And that will work because this number here will be a negative number, and I'm subtracting, so that will add those two lengths together. So I'll get this actual height right here, making this calculation here. Okay, and then as we know, we would have the usual width there, delta x, and the area that I'm trying to calculate between those two curves. We could see that using the definition of the definite integral in this manner here, which would be f at xi star minus g at xi star delta x. And then when I take the limit, that simply becomes this guy right here. Okay, so that does work. So that's why we're going to see here our theorem. We're going to just state this now as a theorem, that the area of a region bounded by two curves, f of x and g of x, and the lines x equals a and x equals b, and we're going to put the conditions on the two functions are continuous, and this one is important. F is always bigger than g. And if that's the case, then we use this formulation here. So we've sort of seen two examples graphically of why that is clearly going to be the right way to calculate that. Okay, notice that area is always positive. Okay, let's do an example. Here's a typical type of example. We want to find the area enclosed by two curves. Notice we're not given the endpoints here. We've been just told find the area enclosed by the curves f of x equals x squared and g of x equals square root x. Okay, so a little bit of caution is required in setting up the integral. Once the integral is set up, the problem is basically solved. So I'm going to draw the two curves. There is f of x equals x squared, and then I'm going to draw the second curve. There is g of x equals square root x. Okay, and I'm asked to find the area enclosed by the two curves. So now that I've drawn this picture, I can see that the enclosed area is sitting right here. Okay, I'm not told the endpoints, but so what I am now that I see what's going on here, I realize that this point I'm going to have to integrate from here, from the two intersection points of the curves. So I need to determine the endpoints. So when we're solving these kind of problems, when we are told to find the area enclosed by two curves, step one is going to be determine the endpoints if they're not already specified in the problem. So determine the endpoints. How am I going to do that? Well, the endpoints are precisely where f of x equals g of x. So in this example, that will be where f of x, it always is where f of x equals g of x. And in this case, we have y equals x squared, or f of x equals x squared, and we have y equals square root x. So I'm looking at where does x squared equal square root x? That's what I'm asking, where? So I put them equal and I solve for x to see what that is. I get x to the 4 equals x. X to the 4 minus x is 0, and I factor out an x and I get x cubed minus 1. And I see that I get from this equation two real solutions, x equals 0 and x equals 1. So I know that, I can see this from my drawing, but that is 0 and this is 1. And then that allows me to calculate this here. Square root of 1 is 1, and of course the 1 squared is 1. So I'm sitting here. So now I know what my endpoints of integration are going to be. They're going to be going from 0 to 1. So that's determining the endpoints. 2, determine which function is the upper function. The upper function. It's not always f of x. That is the word upper. Determine the upper function. Okay, in this case, it is g of x. G of x here is above f of x. You could test this with a number in the interval, because you know there's no intersection points in the interval. That means one function has to be bigger than the other for this entire interval. So you could just test. There's a way of, you could use the graph. That's one method. Or you could test, like for example, take x equals to 1/2, and then you could compute f of 1/2 and find out that that's 1/4, and you could compute g of 1/2 and find out that that is 1 over square root 2, and then you would see that, oh look, 1 over square root 2 is bigger than 1 over 4. So g of x is the upper function. So the answer to this, for this problem, the answer to this question is g of x. So you've determined the endpoints, you determine which is the upper function, and then step 3, you write the integral. And you write the integral in this manner. Sorry about that, bump that. You write the integral in this manner. The integral from the left endpoint to the right endpoint of the upper function minus the lower function. If you do one of these integrals and you get out a negative number, what you should do is, well, you might have made an arithmetic mistake, but if you believe that you've done all the calculations properly, then what you should do is check whether this is correct. Like if you accidentally do the lower function minus the upper function, you're going to come out with the right number, but the sign will be wrong. Okay, so we're going to set that up in this case. So then the area between these two curves is the integral from 0 to 1. That's the left and right endpoint, which we computed. The upper function minus the lower function, dx. Okay, now we've got something extremely simple. So now we can just easily do this in two pieces like this. Okay, so this is a straightforward calculation. So let me just fill in a few of the details here. As we do the first integral, that is 2/3 x to the 3/2 evaluated at 0 and 1 minus x cubed over 3 evaluated at 0 and 1. And you do the arithmetic on that and you find out the area between those two curves is 1/3. Okay, as an exercise, just confirm that both of the other integrals are 1/3. So it's kind of interesting. We just computed that this area here is 1/3, and what I'm saying, that's the area between the curves, and I'm saying that this area is also 1/3, and this area here is also 1/3. I really want to use an X there. This area here is also 1/3. So this area here is 1/3. The area here, let's just call that A1, and area A2 here is 1/3, and we computed that this area is 1/3. Check those other two integrals, set them up properly, think about how to set them up, and then check that the other areas are 1/3. That's a good exercise. Okay, so there we have it, areas between two curves. Let's do one more example where we see that what we have to be careful about when we're doing this. So let's see, we want to find the total area between the curves, between the sine and the cosine curve from 0 to 2 pi. Okay, so that means we want to find this area here. This one plus this one plus this one. Okay, the red line is the cosine, the blue or darker, almost black line is the sine. So we've got the two curves there and we want to find the area between them. Okay, I'm going to call this area in this section A1, this area here A2, and then this area here A3. The thing to notice and the thing to always be careful about, particularly when you don't have a graph sitting in front of you, is that the upper function changes on the interval. We're told we want to do this between 0 and 2 pi. 2 pi is right here. We have to be careful because we can't just subtract cosine minus sine or sine minus cosine because up until this point here, up until that point there, the cosine function is the upper function, and then between this point here and this point here, the sine function is the upper function, and then for the area A3, the cosine function is again the upper function. So we have to be very careful. We can't just write it out immediately as a single integral. Okay, so you're told the interval, but you still have to check for intersections. That's the main point, because there might be an intersection within the interval like there is in this case. So my first step is going to be determine the intersection points. Okay, so that's going to be, where does sine x equal cosine x? And that is at pi by 4. So that is x equals pi by 4. And the next one in the interval that we're interested in is pi plus pi by 4, which is 5 pi by 4. So let's just put those on the graph. This number right here we've now determined is pi by 4, and then this number right here is 5 pi by 4. There it is. Okay, so we determine the intersection points, then we figure out which function is bigger, and then we set up the integral. So now we're like determine upper function, which changes. So we're going to write it out as 3 integrals as a result. Okay. So determine upper function. We can see what that is from our graph. You could also do that algebraically if you wanted to. Step 3, set up the integral. And we will do that right now. So what we're doing is the total area is going to be the integral from 0 to pi by 4. And in the integral between 0 and in the interval between 0 and pi by 4, the cosine function is bigger. So this will be cosine x minus sine x dx. And then in the interval between pi by 4 and 5 pi by 4, the sine function is bigger. So this part will be sine x minus cosine x. And then in the interval from 5 pi by 4 to 2 pi, again the cosine function is larger. So this is going to be cosine x minus sine x dx. Okay, looks a little bit painful to do, but now I mean this is just a calculation. You have to integrate the sine and the cosine. And you have to do a whole bunch of arithmetic. I always attempt to minimize the amount of work I have to do, and so I'm going to exploit symmetry here. This is an effort to try to reduce work. So I'm going to exploit the symmetry, and what do I mean by that? I'm meaning that A2, as I've labeled it up there, this is A2 being this one here, that is actually the same as A1 plus A3. You can sort of see if I took A1, this part here, and I moved it over and I attached it on here, it would be exactly a mirror reflection of A2. So I notice this symmetry that A2 is A1 plus A3. If you don't notice this, of course, going and brute force and just computing this integral, these 3 integrals and evaluating them correctly will get you the correct result. But you can save yourself, by a little bit of thought, you can save yourself this work. So first we notice the symmetry. So that means that the total area is 2 times A2. Okay, and so then I write that as 2 times the integral from pi by 4 to 5 pi by 4 of sine x minus cos x dx. Okay, so that's now put the work into 1/3. So let's go ahead and do that integral. That's going to be 2 times minus cos x minus sine x. And I'm going to evaluate that at the endpoints, pi by 4 and 5 pi by 4. Okay, then something else nice happens that I could notice, and that is sine and cosine have the same value at pi by 4 and 5 pi by 4. How do I know that? I mean, I already know that right here. There's pi by 4. Sine and cosine have the same value. Here's 5 pi by 4. Sine and cosine have the same value. So this calculation, I can just rewrite it. I'm going to factor out the minus sign, minus 2. So that's this 2 and the minus sign. And then I'll have cos x plus sine x, but they are the same. So that's just going to be 2 cos x evaluated at pi by 4 and 5 pi by 4. Okay, let this just sine x equals cos x at pi by 4 and 5 pi by 4. Okay, that's just a time-saving maneuver. And so now I've got it down to just 2 calculations. So this is then going to be minus 4 times the cosine of 5 pi by 4 minus the cosine of pi by 4. There it is. Okay, then let's get those out. Special triangles. We want to be able to evaluate these ones without using a calculator. Almost all the questions we have will be, effectively come out to be the 30, 60, 90 triangle or the 45, 45, 90 triangle. So you should be able to get all the trigonometric functions on those 2 triangles out of your head quickly. So this is, and then of course taking account of the quadrant that you're in. So this is minus 2 root 2 over 2, and then this is root 2 over 2. And I do that and arithmetic, and I get 4 times square root of 2 square units. So in between these two functions, sine and cosine, we find that we have an area of 4 root 2 when we go between 0 and 2 pi. It's kind of actually, in some sense, an interesting result mathematically, I find, because we've got two functions. We haven't talked about this much in this course, but we've got two functions which are transcendental functions. So most of the values of the sine and the cosine are transcendental, and now we've subtracted them, and we've come out with an irrational number, but an algebraic irrational number. So it's kind of interesting. Okay, let's continue here. What happens if we've got a similar question like this one here, and we want to find the area in curved, and our functions are possibly nicely set up so you can list them as x equals y squared rather than, for example, I mean, either one of these functions you could put y equals, like say, plus or minus square root x. In fact, they're not even functions because they don't pass the vertical line test. But we've got, yeah, so I did highlight that for myself. So you notice each one of these are equations. They're not functions because of the vertical line test. But doesn't matter. That means we could still solve for y in both of these cases, and we could. I'm going to erase this after I do it, but we could compute the area this way, thinking of putting in the rectangles this way. Right, so you could then notice what would happen. You have to be a little bit more clever. You would have to notice that what you were doing, calculating the area between the enclosed by these two curves, that up until this point here, you would actually be calculating the area from this part, this function of the x equals 2y squared minus 4 minus another piece of the same function. And then here, you'd have to notice that you were calculating this area here and this area here. And you have to be very careful how you set it up. So that is that method will work. Why don't you try it out? But cautiously set up the three integrals, maybe use some amount of symmetry, and see if you can do that. Possibly better, though, is to look at it this way and imagine stacking your rectangles this way, like this. We're going to take the limit, and we're going to see, look what we could see what the height and there's no space between these, the height and the width of the rectangles look like if I were to put them this way. So you can do vertical rectangles, or you could be thinking of it in terms of horizontal rectangles. And in terms of horizontal rectangles, if I look at this rectangle, the height of the rectangle would be delta y, and the width of the rectangle is y squared minus 2y squared minus 4. Okay, so I can then think of adding the rectangles in this way, and then I consistently have a method of computing the width and the height that is the same for the entire function, and then I would just add up all of my rectangles in the y direction. So I would be thinking of integrating from this point here up to this point here on the y-axis. Okay, so I can see what this point here is. It is 4 minus 2, and then this point up here is 4, 2. I can also see symmetry here that I could calculate half of the area. That would be this right here, half the area here, and then just simply double that. Okay, so now that we have an idea that we could go calculating, integrating left to right using dx, that is one possibility. The other possibility is we can integrate up to down with using dy. So referring back to our sort of steps from before, actually we should have a step 0. We had step 1, 2, and 3, but really now we should introduce a step 0, which is decide if you should integrate like this from a to b of the upper function minus the lower function dx, or if you should integrate from c to d of the right function minus the left function dy. Okay, so we need to make that decision, and in this case we're going to be using this second one. We haven't seen an example like that, so we got to still find the intersection points. I mean, they're on the graph there, but let us just these intersection points, we would find those by setting y squared equals to 2y squared minus 4, and then noticing that that means that y squared has to equal 4, so y is plus or minus 2. Okay, that gives us the intersection points. Okay, so now I'm going to set up the integral in this manner here. So the area between these two curves is going to be the integral from minus 2 to 2. So I'm integrating from here, starting with these rectangles down here, and I'm moving the whole way up, and that's going to be y squared minus, that is the right function, minus the left function. And I'm integrating with respect to y. Okay, then I employ the symmetry that I noticed, and which is that this thing here is half of the total area, so I could integrate just from 0 to 2 and double it, which I will do so that the calculation will be easier. That'll be 0 to 2, and then y squared minus 2y squared is minus y squared, and minus minus 4 is plus 4. So there is the integral that will give me the answer I am looking for, and I'll just complete that calculation. The integral of minus y squared is minus y cubed over 3. The integral of 4 is 4y, and that I'm going to evaluate at 0 and 2. And then that is going to be 2 times minus 8/3 plus 8, and that is going to be 2 times 16 over 3, and that is 32 over 3. Okay, so that is the answer. So if you wish to, maybe even it would help to convince you that the step 0, you should pause and decide which way to do it. I've, in my experience, students prefer to do this because we're sort of used to integrating with respect to x. It seems more natural, but there's no reason you can't tip the rectangles, and so it probably is a good exercise for you to try to do this particular question using this way that you may be inclined to jump to first. See if you can set it up properly. It's much more complicated, and then you know the answer, so you can see whether you've done that correctly. And then notice how much simpler it is to do it the other way. So you want to force yourself to do it the more efficient way whenever possible. Okay, so that's what's captured here in this statement here. The area bounded by the curves. We have x as a function of y, and x as we have x as f of y and x as g of y. So we've got two equations. They don't necessarily have to be functions. And then we have the lines y equals c and y equals d. And then we have the continuity requirement. And then we also have one function being greater than the other for every value of y between c and d, and then we've got an expression for the area. That's the one we just did on the previous example. Okay, so then there's just a kind of an interesting physical meaning of what an enclosed area is. This is something coming from the theory of elasticity. So we imagine a piece of rubber to which we apply a stress. So just imagine a big block of rubber. Maybe I bolt some sort of handles onto it, and I pull, and the rubber deforms and stretches out as I pull on my handles. And then what happens? That's the loading curve. So my rubber is there. I start to apply force. Not too much happens, and then after a while, it gets enough force that the rubber starts to stretch, and it stretches, and I keep pulling, and it goes up like that. And then I decide to stop pulling, and I let go, and I let the handles go, and I let the rubber shrink back to its original shape, and it won't come back on the same curve. This is a factor known as hysteresis. So that's physically what happens. It comes back on a different curve and it ends up back at the same start point. And there's a certain area enclosed between these two curves. Okay, and that area actually tells you how good that physical piece of rubber that you chose, given whatever it's made out of, how good it is at absorbing vibration. So, you know, if you've got somebody in the apartment above you who's making parties every night, you want to put something on your ceiling to absorb the vibrations. You could test out, using this method, test out a variety of materials, calculate this area between the two curves, and then you should mount to your ceiling the one that has the largest area, because that will absorb more of the noise and allow you to sleep better and study more math the next day. Okay, all right. Next part of this lecture, we are going to look at doing the same thing between two curves in polar coordinates. You covered polar coordinates in Calculus 1. Now would be a good time to review them, especially if you thought to yourself, oh no, I was not totally clear on how those things are working, or it came near the end of the course and that was a complicated topic. Or some of you actually might be coming from a flavor of Calculus 1 where polar coordinates was not covered. If that's the case, now's the time to go back. These are not going to go away. They are very useful, particularly for certain types of functions that are symmetric about the origin. Okay, so let us see how this is going to work. Two curves in polar coordinates. So first of all, we're going to recall something important. That is the area of a sector. I'm going to just write it like that. The area of a sector of a circle is 1/2 r squared theta. We're always working in radians. Okay, like degrees should be just sort of flushed out of your brain. We're always going to be working in radians. So I'll just put that here, theta in radians, but I'm not going to always say this. You should assume I'm working in radians, and you should always work in radians unless there's some reason to specify otherwise. Okay, so what does that mean? That means if I have a circle, here it looks like this, and I take a sector, a pizza slice, otherwise known as a pizza slice, and this angle here is theta, and this is like this, x squared plus y squared equals r squared. So I've got it centered at the origin, and the radius is r. Then the area of this pizza slice is 1/2 r squared theta. Okay, and that's the area of a circle. Okay, so we're going to use that to set up the proper integral for calculating the area between curves in polar coordinates. So let's now take a look at a polar curve between two angles. Imagine I have some polar curve. There it is. So the curve here will be specified by some function in polar coordinates. That'll be r, will be some function of theta. Okay, and then this angle here will be theta equals a, and then this angle here will be theta equals b. Okay, so what we're going to be asking for is the area in here. Okay, and the area in there, well, let us imagine I'm going to erase a little bit of this blue stuff so I can make it neater, but that we were trying to find the blue area. Now we're going to imagine dividing this thing up into basically little pizza slices like this, and rather than, and then we see we have an unusual shape here, we are just going to approximate this with a circle of a radius. So this right here, in the same way that we used rectangles before, this is going to be the ith circular sector. Okay, the ith circular sector will have some area. There'll be some area here, and that area, which I'm going to call delta A, increase in the area that I'm calculating up as I move from theta equals A to theta equals B. That area is going to be 1/2 r squared delta theta, where delta theta is this angle here, delta theta. Okay, so I'm asking what small increment in the area do I get from looking at a small increment in the angle, and then here we have that r is a function of theta. And so the area, the total area, will be the limit as n goes to infinity of the sum of all these little pizza slices. That is 1/2 r squared and delta theta I. And indeed, what we are sitting here now looking at a Riemann sum. So that gives us that the area inside this polar curve, that blue thing, will be the integral from a to b of 1/2 f of theta squared d theta. Okay, so basically, instead of using rectangles and then taking the limit of the sums of the rectangles, we're using little pizza slices and then taking the limit of the sum of the pizza slices because we know how to calculate the area of each little pizza slice. Okay, that is exactly what you're being told here. The area of a polar region is 1/2 f squared, f of theta squared d theta, and we sometimes write that with r there, thinking of r as a radius, and r is a function of theta. Okay, so we're trying an example here. That would be we try to sketch this cardioid, 1 plus cos theta, and we've tried to find the area that it encloses. Okay, so first thing, sketching the cardioid. Okay. First of all, use your words always. Sound like a preschool teacher. Use your words. This word here, cardioid, I look at that, I see here the root cardio in here, and then I think, okay, where else have I seen that? I mean, I see like somebody can have a cardiac arrest. So this root cardio means heart, and so hopefully that gives you a little bit of a clue what it looks like before you even start to sketch the graph. Okay, so you want to maybe, if you need, review how to sketch a polar curve. So what I'm going to do first is I'm going to plot r versus theta, and I'm going to draw this as in rectangular coordinates, r versus theta, and that is 1 plus cos theta. So it looks like this. Okay, that's what it looks like. This is a graph of r equals 1 plus cos theta in rectangular coordinates. Okay. Don't get confused. This is not a polar. This is not a polar curve. This is just to let me see what is happening. So this is pi. This is pi by 2, and this here is 2 pi. Okay, so then using that as a little bit of a guide, I draw my axes here like this, and I am now thinking of plotting r as, so I'm seeing theta here, theta increasing here, and then I want to plot what is r for a given value of theta. So I'm starting right here at theta equals 0. I see that r here is 2 because cosine of 0 is 1. So this place right here is 2. So that means I am here. When theta is 0, r, excuse me, r is 2. And then I look at what happens as I go down to pi, the radius goes to 0. So it's basically the radius is decreasing down to 0 as I sweep around like this, and I get to pi. Theta is pi right here. I mean, I've gone around like this, and here theta is pi. Okay. Right, and then I see what happens as theta goes from pi to 2 pi. The radius increases from 0. The radius increases, and it keeps going, and it comes back up to 2. And it looks vaguely heart-shaped when I do this. So this number right here is 2. 1 is right here. This number here, well, this is when theta is pi by 2. So you could easily figure out that here this is 1 plus cosine pi by 2, and that is 1. Okay, so that number there where it crosses the x-axis is 1. Similarly down here, it's minus 1. We sketch the cardioid. Now we're being asked to find this area. Okay, immediately by symmetry, you can see that it is double this. I could calculate this area here and then multiply by 2. That's what I'm going to do. I've sketched it. You could review back the Calculus 1 sketching polar curves. So I'm going to exploit the symmetry. I'm going to write out the integral. The integral is 2 times the integral from, now this is, you don't necessarily have to write this, but I'm going to write this to try to be clear. Theta is going to start at 0, and theta is going to go to pi. A common mistake of students to make is to put the limits of integration, I don't know, from 0 to 2 or from 0 to 1. We're not thinking of it that way. We're thinking of going like this, and theta is going like this. And we're adding up all of these pizza slices as theta is sweeping from 0 to pi. Okay, of what do I add up? 1/2 r squared d theta. Okay, so that's going to give me the area of that cardioid. Make sure that this is r squared. You square the whole thing. Okay, another trig identity to make integration easier. I'm going to use this trig identity. Cos squared theta is 1/2 1 plus cos 2 theta. Okay. Trig identities, some of them are incredibly useful to make integrals easier to figure out. Okay, so let me expand this thing right here. I'm still going from 0 to pi, and the 2 and the 1/2 cancel out. That's nice. And I'm expanding this thing here, so I get this guy here. I get 1 plus 2 cos theta plus cos squared theta d theta. Now I've got 3 integrals to do, but before I do anything, I'm thinking cos squared. Not so easy just to integrate. What would be the integral of cos squared? I don't easily see that. I see it much easier to integrate cos 2 theta, so I'm going to use that trig identity. So I'm just going to keep going down here. I'm going to be 0 to pi of 1 plus 2 cos theta. That's the first 2 terms. And then the cos squared I'm going to replace with 1/2 plus 1/2 cos 2 theta d theta. And then I am going to combine this and this because that's going to just make my life easier. And then at the same time, I'm going to split this into 3 integrals. So it's going to be 0 to pi of 3/2 d theta plus the integral from 0 to pi of this one, 2 cos theta, plus this one, the integral from 0 to pi of 1/2 cos 2 theta d theta. Okay, all 3 of these integrals straightforward, and then now we're into the evaluate the integrals, do the arithmetic, etc. So let me just do that. 3/2 theta evaluated at 0 and pi plus 2 sine theta evaluated at 0 and pi plus 1/4 sine 2 theta evaluated at 0 and pi, and I do all that arithmetic. Please, so there's arithmetic now. Please do this yourself. Don't just say, "Oh, I trust her." First of all, I make mistakes, and secondly, it's really good for you to practice. You know, evaluate them. You get faster and more confident the more practice. So anyway, I when I did this, I got 3 pi by 2. Okay, so main point here is to understand how to look at this. If you've got an equation, a polar curve, in using polar coordinates, how to properly compute area. Okay, so that was just inside the cardioid. We can actually now do this if we wanted to try to find the area between 2 different polar curves. So here's that same, it's the same cardioid. I'm noticing it goes out to 2. The same cardioid in red, and then there's a circle in blue, and we want to know what is the area inside the cardioid and outside the circle. So first we're careful to identify what area we're asked to compute. Inside the cardioid and outside the circle. So that is this area right here. Okay. The reason this example is chosen, actually, I'm just going to say this briefly. You can it is the case that if you stick up a single transmission tower, like you're going to broadcast a radio signal, if you stick up a single tower like that and you mm, you power it, it will broadcast and it will broadcast like this, and then those are the people, the area around your this will be a representation of the people who can pick up your radio station. It is possible actually to then, instead of putting up one tower, to put up two towers like this and broadcast on both of them, and that will give you a broadcast pattern that looks like this, the cardioid. Okay? So, and then the people that could hear you would be these people. Now, in the situation where like in Vancouver, these things can be put up on the North Shore, just into the mountains where people are not living. And then if you do this situation, you broadcast, let's say, over here towards Vancouver, but all of this is lost. You know, there's nobody listening. There's no houses. There's nobody listening to you in the mountains. So then you have a choice of maybe doubling your installation cost, using the same transmission power, and then you don't waste so much energy transmitting to people in the mountains, and you transmit much more of your power to the people of Vancouver, resulting in more people being able to hear you for the same operational cost. And in fact, the more people that can hear you are precisely the people who are inside the cardioid but outside of the circle. So this kind of a possible application of calculating an area like this. Okay, so next thing we need to do is identify these endpoints, okay, these ones right here. We have to understand what angle that is. So I want to know what angle that is, and then clearly this angle will be the negative of that. So see this nice symmetry. Okay, so I wanted to figure out what those two angles are. We already know the area of the cardioid is 3 pi by 2. We figured that out from before. So, oh, and in fact, the problem is what we wanted to, in fact, I sort of find the area inside the cardioid and outside the circle. That is true. And we also want to find the circle centered at the origin. I mean, that blue circle is, we've been told, it needs to have the area equal to that of the cardioid. Okay, so we don't actually yet know the equation of the circle, but we know that the area of the cardioid and the area of the circle are equal. So that means our area of our circle must be equal to 3 pi by 2, because that's the area of the cardioid. Okay, and then we know how to calculate the area of a circle. That's pi r squared. So that allows us to figure out that the radius of this circle is square root 3/2. Okay? And that is approximately 1.225. Okay, that's telling me that this point right here is r equals 1.225. Okay. All right, so we've got the circle centered to the origin with equal equal area to the cardioid. Now we want to see, you know, how many more people effectively can hear us, these people. So we want to calculate that difference in area. So we need to find the intersection points. So we've got the equation of the circle. So here's the circle. The equation of a circle in polar coordinates is r equals square root 3/2. That's the equation of that circle. And then we have the equation of the cardioid. That is r equals 1 plus cos theta. Okay, same way we would find an intersection point. The intersection points are are when the radius is equal. So we would stick. Oh, sorry, a little hiccup in the video there. So we're finding the intersection points between the circle and the cardioid. So the circle has equation r equals root 3/2, and the cardioid has equation 1 plus cos theta. So we're putting r equal. That will mean that we have cos theta, cosine theta equal to square root 3 over 2 minus 1. So I'm basically, r is equal, so these two things are equal. So that means that the cosine theta is equal to this, and I'm good doing this with a calculator. So the cosine of theta is 0.225. So theta in radians then, theta is 1.344 radians. That is the first quadrant intersection point. So this angle right here, this theta right here is what I just said, 1.344. That is this angle right here. And this angle right here is theta equals minus 1.344. You can see that from the symmetry. Okay, so now I can set up the integral to make this calculation. The area inside the cardioid and outside the circle is going to be 2 times, that's the symmetry, 1/2 the integral from 0 to 1.344 of 1 plus, this is r squared, the outer function, so this is the cardioid, minus the circle, which is on the inside. So that's going to be, oops, that's a minus sign, minus the 1/2 the integral, same. I could have put this together in one integral. That's this is here, r squared d theta. Okay, so I don't know. This is now a computation. Let us do some portion of that. I'm trying to think here what exactly I want to do. So that 2 and the 1/2 is going to cancel out. This 2 and the 1/2 like that will cancel out. I've got the 1 plus cos squared. I've already done this in the previous example, so I'm going to just use that information here. So the previous, when I was calculating the area inside the cardioid, these calculations were made. So I'm going to bypass a couple of steps here. Nice, would be a nice idea for you to fill those all in again. So this is going to then be 2 sine theta, 1.344, plus sine 2 theta over 4. I use that same trig identity. So this is replicating the calculation from before. And then I'm subtracting 3/2 theta, which is this integral here, from 0 to 1.344. Okay, nice cancellation there. That leaving me then with the area being, I have to evaluate if to use the arithmetic here. I will come out with the area of 2.0581. So that is the area inside the cardioid but outside the circle. So this is inside the cardioid and outside the circle. All right. So if we look at what that is, I mean, we found that the area of the cardioid, let me just pull that like that, a card. The area of the cardioid we found previously was 4.712. And we know that though the area outside the cardioid and inside the circle, inside the cardioid and outside the circle, so we can then calculate the percentage of area, the percentage of the area of the cardioid outside the circle is 2.058 divided by 4.712 times 100, and that number comes out to be 44%. So I mean, in the example that the physical example that I said, you imagine how many more customers you can reach with the same power transmission if you use a double tower system over a single tower system. That would be 44% more people could hear you. And so you may wish to then, look at the cost of doubling the installation cost, and then look at how much you're saving on power transmission and then decide whether you wish to do one or the other. So that's a sort of practical reason for finding something like this out. And then the final point I want to make here is that we need caution when finding the intersection points in polar coordinates. So caution. Finding intersection points in polar coordinates can be problematic. Finding intersection points in polar coordinates can be problematic. So you need to be thinking clearly, and you may be using a graph to make sure that that you're seeing what's going on. So a visual picture can be really helpful. And the reason why this happens is you can miss an intersection point when you're solving the equations, and that part of the reason for that is like in polar coordinates that every point has multiple representations, and so you want to be careful that when you're solving these equations, given that a point can have multiple representations in polar coordinates, that is unlike in rectangular coordinates, it is possible to miss an intersection point, and a picture, a drawing, helps you to minimize the chance of that occurring. Okay, that concludes this section, 6.1 and 10.4. I will be back shortly with the next installment. Thank you.